So how are we all doing here? Do you feel like you had success? I think this can be an easier difficult problem depending on your experience and how comfortable you feel with this stuff. So let's work through it together here. So we've got this polynomial f of x equals x squared plus 2x plus 2, which we're considering to be in this ring, this polynomial ring. It is quadratic, so it's enough to check that it has no zeros in Z3 to confirm that it's irreducible over Z3. And as we know, that means that when I form this factor ring, it's actually a field, because f of x being irreducible means that this principal ideal generated by f of x is a maximal ideal, and that makes this factor ring a field. And we've seen also by doing long division that you can, when this is quadratic, this is going to be a linear representative that you can use. If it were cubic, then you can use a quadratic representative. It's always 1 degree less. If it were a 4th degree, then you can use a cubic. But this is 2nd degree, so we can use a linear representative. Technically, this factor ring does consist of things that are cosets, elements that are cosets, where this is linear and A and B are in Z3. So you've got 3 choices for A and 3 choices for B, making this field have 3 squared or 9 elements in it. But that's not the way the problem is phrased. It just says some extension field of Z3. And they even call the extension field Z3 adjoin alpha, where alpha is some other, evidently the 0. And they're not saying it's a coset. So what's really going on there? Well, it was proved, it's a theorem, that any extension field where you've adjoined a root here is going to be isomorphic to this. And so effectively, when I take Z3 of alpha, Z3 adjoin alpha to be this set, it's like I'm essentially just looking at coset representatives here. Though it is traditional to use alpha instead of x, I started to use x because I was thinking about the coset representatives, but use alpha as acting like the x does up here. Because we did see with an example, and you also read about with Kroneker's theorem, that one example of a root of this polynomial in this field is when I have the representative x plus the ideal generated by f of x would be one example of a root. And so effectively, it's like the x becomes the alpha. But if I'm using an alpha here, I better use alphas in here. But it's like it's an x, and these are like the coset representatives. So you got 9 elements here. We could form a multiplication table, for example, is something we could do. We want to keep in mind that alpha is assumed to be a root of f of x, so alpha squared plus 2 alpha plus 2, by assumption, really, is equal to 0. Solving for alpha squared would be negative 2 alpha minus 2, but then mod 3, that's going to be the same thing as alpha plus 1. And that's something you need to use. But our task is not to make the multiplication table. You can see our task is to find the other 0 of f of x in this field. And I said the quickest way to do it is with synthetic division. One root is alpha, so x minus alpha would be a factor, which can also be written as x plus the additive inverse of alpha, whatever that happens to be. Put the coefficients of the polynomial under the bar here. The original polynomial, 1, 2, and 2. And do your synthetic division. And if you do it right, and if you think about using this fact, should get a remainder of 0 in the end. Bring that first number down, put it there. Multiply, alpha times 1 is alpha. Add. Multiply. And add. And this last thing is 0. That's what we wanted. We wanted a remainder of 0. So, and look at these things. These are the coefficients of the factor. This means I can factor x squared plus 2x plus 2. Well, if I want to use minus signs, I can write x minus alpha times x. Well, here there's no minus sign. It's alpha plus 2 plus alpha plus 2. Oops, excuse me. Okay, no, that's right. Okay. So what is the other root? The other root is evidently negative alpha minus 2 mod 3. That's going to be 2 alpha plus 1. Did you get that? 2 alpha plus 1 is the other root. This synthetic division, by the fact that this is 0, because I'm assuming alpha squared plus 2 alpha plus 2 is 0, does mean that alpha is a 0. And it also means, looking at these numbers or these expressions, that those are the coefficients of the other factor. And by the fact that I can factor it like this, that means negative alpha minus 2 is the other 0 of this. That's going to make that 0. Mod 3, that's the same as 2 alpha plus 1. This factor, I mean, it's okay to write it as x minus alpha. Maybe better to write it as x plus 2 alpha. So that the coefficients stay in Z3 in this ring here, or in this field, Z3 alpha. The other root is 2 alpha minus 1. If you want extra confirmation, you could multiply x plus 2 alpha times x plus alpha plus 2 and see if you get the original polynomial when you simplify. We get an x squared, we'll get a plus alpha x plus 2x plus 2 alpha x. X times x is x squared. The alpha x comes from x times alpha. The 2x comes from x times 2. The 2 alpha x comes from the product of these two right here. Then I'm going to also have a plus 2 alpha squared, this one times this one, and then a plus 4 alpha. Mod coefficients by 3, and also use the fact that alpha squared, just like before, is alpha plus 1. This thing can be replaced by an alpha plus 1. So we get x squared. What's the x term? Comes from here, 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 and okay, those 3 terms give you the x term. It looks like that's going to be, well, 2 alpha plus 2 alpha is going to be 3 alpha, which is 0. Right? Mod 3. So the only x term is the 2x term right there. This cancels with that. What about the constant term? That comes from these 2 terms. Initially, if I multiply this by 2, I get 2 alpha plus 2, but then a 4 alpha. 4 alpha plus 2 alpha is 6 alpha, which is 0, mod 3. This cancels with that. And you're left with x squared plus 2x plus 2, the same polynomial that we started with. Tricky, very easy to make a mistake and be confused because you made a mistake. But if you can avoid mistakes and get it, also kind of like the author emphasizes, finite fields are kind of fun and in a mathematician's kind of way. It's fun to see it work out when you fixed your mistakes. All right, for the rest of the day today, we're going to get into Galois theory, the last topic for the course. Let's start simple and build up toward more complicated through examples. Okay, that's with pretty much everything in math, that's the best way to learn initially is through examples. So here's our example. The field Q adjoin, oh, let's make it say square root of 7 is a field extension of Q. We knew that already. I can draw a tower of fields if I like. Q adjoin root 7 being above just plain old Q. That's one way to visualize this. I could also draw a Venn diagram, this representing Q, this representing Q adjoin root 7. And I could also ask a question. In this tower of fields or in this diagram, are there any fields between Q and Q adjoin root 7? In other words, i.e., does there exist a field call it E with Q adjoin Q being a subfield of E but not equal to E? That means subset but not equal to. And with E being a subfield of Q adjoin root 7 but not equal to it. That's a question you could ask and wonder about. And according to Galois theory, the answer would be no, there is nothing strictly in between these. But how does Galois theory imply that? What about Galois theory, which, by the way, is chapter 32? We're skipping from chapter 22 all the way to chapter 32. We have what we need. We don't need the intermediate chapters. But why is this no, according to Galois theory? To start to construct why the answer is no, according to Galois theory, we need to construct what's called the Galois group of this field over that field. Symbolically, it's written as Gal, in honor of Galois, of the field extension Q adjoin root 7 over Q. Now, it's tempting to look at that thing there and say, hey, I guess that must be a factor ring. But no, it's not. This is not a factor ring. It's just notation. It's just part of this notation, okay? Not a factor ring. Well, remember, fields never have any non-trivial ideals anyway. So you're never making factorings with fields. You can make a factoring into a field like we did with our first example today. But you're never taking a field and using an ideal of the field to make a factoring. I mean, you could, but it would be trivial because the only ideals would be just the trivial subring and the entire field itself. So that's something you never do with fields. You never make factorings with them. This whole symbol represents something called the Galois group. Here's how you spell Galois. Galois group of Q adjoin root 7 over Q. But what is it? What is the Galois group? It's a group of automorphisms. Oh boy, back to automorphisms. Not group automorphisms, ring automorphisms. The group of ring automorphisms, I also could call them field automorphisms because these things are fields, but every field is a ring. Of Q adjoin root 7 that keep the elements of Q fixed. Consider all possible automorphisms of Q adjoin root 7. In other words, what is an automorphism? It's an isomorphism from, in this case, Q adjoin root 7 to itself, right? One-to-one onto mapping. That's also, well, it's a ring automorphism, so it's doubly operation preserving. It preserves both addition and multiplication. Which of those automorphisms keep the elements of Q fixed? In other words, i.e., if I call such an element phi of x equals x for all x in Q. What would be the, if this is a group, what do you think is the group operation? The elements are functions. Could I add these functions? Could I multiply them? Technically, you probably could, since their outputs are real numbers, but that's not the operation. What's the only other possibility besides addition and multiplication when you combine functions to form function composition? Yeah, the operation, and we're only considering one operation, is function composition. Funny thing historically is Galois lived back in like the early 1800s and died very young. It's a sad story. He died in a duel, I guess. One story has that it was political, and one story that it was that it was over a woman. But he died young, like at 22 or something. But he did all this stuff, and he did it like 60 years before group theory was developed. Wait, how can that be? How could Galois be doing group theory before group theory was developed? Well, he was doing a rudimentary form of it, you might say. It was not the fully abstract form that we learn about in this class. He was thinking about elements that were functions and composing them, and he noticed that they closed under function composition, and function composition is associative, and there's an identity element. The identity element is going to be the identity automorphism. Map everything in Q root 7 to itself. That will also map all elements of Q to themselves. And every such function also evidently has a multiplicative inverse in this thing. He didn't, I think actually he did use the word group in, well, he was French, in whatever the French version of the word group is. Group of, I don't know that he used the word automorphisms. Permutation, perhaps. Actually, these things are related to permutation groups. So he was doing group theory and field theory before the abstract theory was developed. But he was essentially on the, it's the same ideas, just with different terminology, different notation, and that kind of thing. So it is worth giving him credit for this. You might ask, why was Galois doing this? He was trying to prove ultimately that quintics, fifth degree polynomials are not solvable by radicals. Quadratics certainly are, because you've got the quadratic formula. Turns out that cubics and quartics, third and fourth degree polynomials, are solvable by radicals, though I will tell you that if you ever look up the formulas for those things, they are crazy complicated. Much more complicated than the quadratic formula. But fifth degree and higher, it turns out, in general, are not solvable by radicals. This is a classic problem. People were trying to solve them by radicals, but even though you could solve them in special cases, you couldn't solve them in general. That was the problem. So coming back to this thing, what is it here? What is this Galois group? What's it isomorphic to, for example? Is it finite? It turns out it is finite. Let me just tell you what the answer is here in this case. In fact, it's a two-element group. Call the elements epsilon and alpha. Epsilon for a reason, because it's like the identity permutation back in chapter 5, where epsilon of x equals x, not only for all x in Q, but for all x in Q adjoin root 7. And what is Q adjoin root 7 anyway? Well, remember, it's going to be a vector space over Q, and root 7 has minimal polynomial x squared minus 7 in Qx. That has degree 2, so a basis for this is going to have two elements, 1 and root 7. You can write all the elements as, write them the other way this time, C0 plus C1 root 7, where C0 and C1 are in the base field Q. So I also could have written the formula for epsilon as epsilon of C0 plus C1 root 7 equals C0 plus C1 root 7. What does alpha equal? What does alpha apply to an arbitrary element C0 plus C1 root 7? Well, if it's going to keep Q fixed, the Galois group is the group of field automorphisms of Q root 7 that keep all the elements of Q fixed. Alpha's got to keep the elements of Q fixed as well then. In other words, for example, if C1 is 0, if the element is just C0, the output better be C0. If it's going to keep all the elements of Q fixed. But is that the answer? No, that's not the answer. That mapping is actually not going to be an automorphism. What should I map this part to, so to speak? Turns out you want to map it to minus C1 root 7. Though I haven't explained why. Why? What should alpha of root 7 be in general? For a general automorphism, not necessarily this automorphism. Well, let me write it differently then. For an arbitrary, call it beta, in this Galois group, what should beta of root 7 be? Just a plain root 7. Well, do this calculation. Take beta of root 7 and square it. Which I can do because beta of root 7 is a real number. It's in Q adjoin root 7. I can certainly square that number. I'm not doing the function composition operation here. In other words, I can think of this as beta root 7 times beta root 7. And since beta is an automorphism of Q root 7, it's doubly operation preserving. This should be the same as beta of root 7 times root 7. In other words, this should be the same as beta of root 7 squared. In other words, it should be the same as beta of 7. But what's beta of 7? Well, 7's a rational number. Beta's got to keep the base field elements fixed. That's what the Galois group does. It keeps the elements of Q fixed. Beta of 7 has got to be 7. In fact, you could say that that's got to be true for any automorphism of any extension field for Q, whether it's a priori in the Galois group or not, because problem number 1 in chapter 32 says this: let E be an extension field of Q, any extension field of Q. Show that any automorphism of E acts as the identity on Q. In other words, it turns out it's got to be in the Galois group of E over Q. Any automorphism of E will automatically be in the Galois group of E over Q, not necessarily E over some other field between Q and E. It won't necessarily be in the Galois group of that. But because any automorphism of E acts as the identity on Q, it will automatically be in the Galois group of E over Q. Kind of confusing, but true. And you may use number 1 whenever you need it. So this is definitely true. Beta of 7 is 7. 7's a rational number. So what do we have here? We have beta of root 7 squared equals 7. In other words, beta of root 7's got to be one of the 2 square roots of 7, which would be plus or minus square root of 7. Therefore, beta of root 7 is plus or minus root 7. And coming back to the actual elements, the symbols that I used, epsilon and alpha, epsilon is the one that maps root 7 to itself, because the plus sign here and here, those 2 plus signs match. And alpha is the one that maps root 7 to negative root 7, because this plus sign changed to a minus sign. That's why there's 2 possibilities, 2 elements in the Galois group of Q adjoin root 7 over Q. These 2 functions right here. I was trying to answer why with all this. Why does alpha have to have this kind of formula? You might wonder, is alpha really doubly operation preserving? Is it really an automorphism? It's pretty clearly 1-to-1 and onto from Q adjoin root 7 to itself, because the elements of that Q adjoin root 7 look like this. I'll let you think about that. It's pretty easy to show it's 1-to-1 and onto. Is it operation preserving? Let's check that. Is alpha of say C0 plus C1 root 7 plus D0 plus D1 root 7, is that the same as alpha of the first thing plus alpha of the second thing? So it would be operation preserving of addition. Well, you've got to actually add these things. You're going to get C0 plus D0 plus, in parentheses, C1 plus D1 times root 7. That's how you would add those elements. And the formula for alpha says this is going to be C0 plus D0 minus C1 plus D1 times root 7. And yeah, that is definitely going to be the same as alpha of C0 plus C1 root 7 plus alpha of D0 plus D1 root 7. Because this is going to be C0 minus C1 root 7 plus D0 minus D1 root 7. And yeah, you can rewrite that like this. These are the same. So it definitely preserves addition. Does it preserve multiplication? That's a little trickier in general. Alpha of C0 plus C1 root 7 times D0 plus D1 root 7. First do the multiplication. That's alpha of the part that is not next to the root 7 will consist of C0 times D0, but also from foiling here, last times last is going to be 7 times C1 D1. And the part that does involve the root 7 will be a C0 D1 plus C1 D0 root 7. I foiled there to get from here to here. First times first, outside times outside, inside times inside, and last times last, and rearranged. And by the formula for alpha, this will be then C0 D0 plus 7C1 D1 minus C0 D1 plus C1 D0 root 7. Do I get the same thing if I do this? Multiply the outputs of alpha applied to each individual input. Let's see. The output of alpha applied to C0 plus C1 root 7 will be C0 minus C1 root 7. And alpha applied to this D element, D0 plus D1 root 7 will be D0 minus D1 root 7. Now foil that, you get the part that does not involve the root 7 will come from first and last. First times first is C0 D0. Last times last, 2 minus signs make a plus. Plus 7 C1 D1. Hey, that matches. Those two things match. What about what I get from the outside and inside products? Well, in both cases, there's a minus sign. C0 times D1 is outside times outside. And inside times inside is C1 D0. Don't forget about your root 7. And so these match. Done. It preserves multiplication as well. Alpha is doubly operation preserving. Being a two-element group, it's got to be cyclic of order 2. It's got to be isomorphic to Z2. And its lattice of subgroups is going to be very simple. Sorry. Its subgroup lattice is very simple. It's just this. The entire group, isomorphic to Z2, and its trivial subgroup, isomorphic to Z1. We hardly ever talk about Z1. That's just the trivial group, one element group. The fundamental theorem of Galois theory essentially says that this subgroup lattice corresponds to fundamental theorem of Galois theory. So many fundamental theorems. Says this corresponds to a tower of fields and a particular tower of fields that I already drew for this example where, well, I drew it in the ordinary way, but in a sense, it also would have been okay to draw it upside down. In other words, put the bigger field on the bottom and the smaller field on the top. Because under this correspondence, the relationship gets flipped. It turns out that the trivial subgroup of the Galois group is in some way corresponding to the bigger field. And the bigger subgroup, the entire Galois group, corresponds to the smaller field. What is this correspondence? In general, given a field extension, E of F, and a subgroup H of the Galois group of E over F, we can form something called the fixed field of H. E sub H, it's the set of everything in the Galois group that not only fixes all of F, but also fixes all of H, or excuse me, all of, let's see. Well, this is wrong here, sorry. This is the set of everything in E that gets mapped to itself under elements of H. That's the general idea of a fixed field. I forgot the word field here. Fixed field of H. Venn diagram. Here's F. Here's E. The fixed field of H in general is going to be a field extension of F that's also a subfield of E. H is a subgroup of the Galois group. H is not a field. H is a subgroup of the Galois group, so it does consist of automorphisms of E that fix F, but they also could fix more than elements of F. They could fix other elements this fixed field of H is everything in E that gets mapped to itself by elements of H. Relating this to our simple example, what is the fixed field of the Galois group? The entire Galois group? It's all of Q. Epsilon and alpha both map all the elements of Q to themselves. Epsilon was the identity mapping, and alpha, yeah, if C1 is 0, so that this is a rational number, just C0, its output is going to be C0. It's going to fix Q. It's going to be Q, the fixed field of, kind of funny notation here, but the fixed field of the entire Galois group, epsilon alpha is Q. What's the fixed field of just a trivial subgroup? Epsilon is the identity on E. The formula for epsilon is that epsilon of x was equal to x for all x in this field extension, Q root 7. Another way to think of it is this. It's mapping everything to themselves, so its fixed field has to be the entire larger field, Q adjoin root 7. This fundamental theorem of Galois theory says that since there are no other subgroups in the subgroup lattice, there are no other fields in this picture. So this is coming back to our original question. Are there any fields between Q and Q root 7? And the answer is no. But to prove it, it's based on the fundamental theorem of Galois theory and the fact that this is the entire subgroup lattice for the Galois group. Right there. It's only got 2 groups in it because it's such a trivial group. It's just a 2-element group. We only have 11 minutes left. So we don't have, in one more example here, we don't have time to go into as much detail. But let's try to summarize what would happen in a more complicated example. Say we were trying to figure out the, well, whether there were any other fields in this subgroup lattice not a subgroup lattice, but a tower of fields. Are there any other fields that I could put in this picture? Or any other fields that are in these spots as well? By the way, before I answer that question, I should say one more thing about the simpler example. This is coming back to the relationship between degrees of field extensions and Lagrange's theorem. The degree of this field extension is 2, because Q adjoin root 7 is a 2-dimensional vector space over Q. And the index, remember our old friend, the index? Of this group, the entire Galois group, well, of the trivial subgroup in that entire Galois group is 2. There are 2 left cosets that I could make for this subgroup of this one, because this has twice as many elements as this one does. So it's more than just the association between the subgroup lattice and the tower of fields. There's also an association between the degree of the field extension and the index of this as a subgroup of that. So the fundamental theorem of Galois theory says even more. Are there going to be any other fields that you could put in this picture? The answer is going to be no. What is the Galois and why is the answer no? That can be answered with the Galois group of Q adjoin root 5, comma, also root 7 over Q. It turns out that this is a 4-element group. It's got the identity mapping. It's got 3 other mappings. Call them alpha, beta, and alpha compose beta. Where, as usual, well, epsilon of x equals x for all x in Q adjoin root 5 and root 7. But what do these other things do? I should probably say how to describe elements of Q adjoin root 5 and also adjoin root 7. Turns out this is going to be a 4-dimensional vector space over Q. The elements of this field can be written as C0 plus C1 root 5 plus C2 root 7 plus another term, C3 times, it turns out, root 5 times root 7, which is root 35. Root 5 times root 7. It's going to be root 35. Where all these C's, C0, C1, C2, and C3 are rational. You're trusting me on this, that this is true. I.e., Q adjoin root 5 and root 7 is a 4-dimensional vector space over Q. This degree is 4. Coming back to the Galois group, what are these functions? Well, epsilon is the identity function. It's mapping everything to itself. What about these other mappings? What's alpha of an arbitrary element? Just like in the previous example, we have this calculation here. Beta of root 7 squared had to equal 7, and therefore beta of root 7 must be plus or minus root 7 in that example for a general element of the Galois group, call it beta. So must a general element of this Galois group map root 5 either to plus root 5 or minus root 5, root 7 either to plus root 7 or minus root 7, and also root 35 either to plus root 35 or minus root 35. However, not all those possibilities actually happen. They've got to be consistent with each other in some way. If, for example, alpha is taken to map root 5 to negative root 5, but root 7 to positive root 7, then root 35 is forced to map to negative root 35. Why? Because alpha of root 35 would be the same thing as alpha of root 5 times root 7. And since alpha is doubly operation preserving, this would be alpha of root 5 times alpha root 7. I'm assuming root 5 gets mapped to negative root 5 and root 7 gets mapped to itself. Therefore, root 35 has to get mapped to negative root 35. If I assume root 5 gets mapped to negative root 5, root 7 gets mapped to itself, then I'm forced to conclude, since alpha must be doubly operation preserving, that root 35 gets mapped to negative root 35. Beta can be taken to be a mapping that maps, well, all the rational numbers to themselves. So C0 is always staying C0. Let's say beta maps root 5 to itself, but maps root 7 to negative root 7. Then once again, for the same reason as the previous line, root 35 has got to get mapped to negative root 35. For the same reason as this one here. Except the minus sign would be in front of the root 7 instead of in front of the root 5. But you'd still get a minus sign there. Finally, what does alpha compose beta do? And I'm just realizing that maybe my answer to this question of whether there were other fields is I said the answer was no, but maybe the answer is yes, because I'm realizing the subgroup lattice is going to be bigger than this. So I was a little too cavalier. Let's say, well, okay, what does it map root 5 to, for example? Beta maps root 5 to itself, but then alpha maps root 5 to negative root 5. So alpha compose beta is going to have to map root 5 to negative root 5. Root 7 under beta gets mapped to negative root 7. Under alpha it gets mapped to itself, and also negative root 7 would get mapped to itself. Therefore, alpha compose beta is going to map negative root 7 to negative root 7, or positive root 7 to negative root 7. And if alpha compose beta maps root 5 to negative root 5 and root 7 to negative root 7, it's got to map root 35 to itself, actually. Both of these formulas for alpha and beta map root 35 to negative root 35. So when you compose them, the negative sign gets in there twice, and you get a plus sign. Turns out each of these functions as part of this group has order 2, and this group is isomorphic to the external direct product of Z2 with itself. And if you draw the subgroup lattice, it is actually more complicated than this. And in fact, that means the answer actually must be yes, there is another field in this picture, though I'm not sure what it is offhand. The subgroup lattice is going to look like this, because all those non-identity elements have order 2. To figure out what the other group field is in this tower of fields that I have not mentioned yet, I would have to figure out fixed fields for these subgroups of the Galois group. But we're out of time, so we'll do that on Friday. Okay. Examples, examples, examples. That's the way to go. Have a good day.